Welcome to the second tutorial in the Getting Started with Numerus series. In this tutorial, I'm going to build a simple population model using the Numerus modeling software. This tutorial presumes you've already viewed the first tutorial where I went over the different parts of the Numerus interface. In general, there are 5 or 6 steps in developing a model. The first thing we need to do is think about the system we're trying to understand. What parts we need to keep track of. So for example, in a population model, you have to ask yourself questions like, do we need to keep track of each individual? Or can we just model the entire population? Or maybe we want to keep track of different groups of individuals according to age or sex or other factors. We also need to understand how each population behaves with respect to other dynamics of the system. If we are in a predator-prey system, for example, we know that predators eat prey and thus reduce their numbers, but we also know that when prey declines, so do the predators because there's nothing to eat. And so with the decline of predators, there's a resurgence of prey, and so on the cycle repeats. We also need to determine what to include in the model and what becomes part of the exterior environment or frame. If some quantity flows in or out of our system, do we care where it comes from, where it's going? Or can we treat it as an infinite source or sink, effectively outside the scope of interest? What we include and what we leave out is crucial to the design of the model. The next step is to come up with some sort of mathematical and/or pictorial representation of the system based on how we decided to represent it. After that, we are ready to design the model in Numerus using the graphical modeling components like stocks and flows, and then we can run the model and examine the results of the simulation and how those results change under different scenarios. It is crucial to validate the model against the real-world system that is being represented, and if necessary, make modifications to the model and rerun the simulation, and then repeat this cycle as often as necessary. For this example, we're going to build a simple population growth model for an organism like bacteria and keep things simple. We are only going to concern ourselves with the total population, and furthermore, so we don't have to worry about fractions of a bacterium or limit ourselves to the whole numbers. We are going to measure the population size not as a number of individuals in the population, but as a total biomass, so that fractions are okay. Finally, we're going to pretend that our population grows by a fixed percentage, k, every time step. K can be 10% or 15%, for example. And a time step could be seconds or minutes or hours or whatever is appropriate. Obviously, this isn't biologically sustainable because sooner or later you run out of food or space, but for short periods of time, it's reasonable. We'll use one variable, p, to represent the total population biomass at any given point in time. Now, let's assume the population change is 10% of the current population, or 0.1 times p. So from considering how the objects in our system change over time, we came up with a mathematical representation. For those of you familiar with calculus, the proper mathematical description uses a differential equation. dp dt equals 0.1 times p. Numerous simulations are built from components that abstract the dynamic behavior patterns found in our model. For this model, we'll use 3 types of components. The first of these is called a stock. A stock represents some quantity that is varying over time. We can imagine a stock as being like a reservoir that is both filling and possibly draining according to some property of the model. We abstract the filling and draining using a flow, which we imagine to be some sort of pipe that moves the stock's content to or from the stock or from one stock to another. Finally, since we may need some intermediate values that are computed from the current state of the model, and are required in order to determine how the stock values change, we have a component called a term in which we may specify any such computation. We're now ready to start building the model. We begin by clicking the Components tab and drag a state component from the list to the model canvas. We rename it Population, as this will be our population stock. Next, we drag a flow to the canvas, and similarly, we'll label that flow Growth. And finally, we'll drag a term and label that term Growth Rate. We need to connect the outflow side of growth to population, and this is done by dragging the cloud on the right of growth over population and dropping it. The cloud to the left of growth will remain unconnected since we are not modeling the population source. Next, we would like a way of showing how growth depends on both current population and growth rate. This is done using connectors. We visit the Tools menu and click on Add Connector. We then first click on Population as the source of the connector, followed by Growth as its target. The connector appears as dashed lines since we have actually specified how growth depends on population. We similarly visit Tools again and make a connection between growth rate and growth. We are now ready to specify the behavior of these components, starting with growth. From our earlier analysis, we decided that growth is given as growth rate times population. We click on Growth to reveal its Properties pane, which contains a text area called Value, where we will type in this equation. Because we made the earlier connections, there is a Connections menu showing both population and growth rate. We can select from this menu when entering the equation to ensure that both dependent components get used. Notice that the dashed line of the connectors have become solid lines. This is because we've actually used population and growth rate in our formula. Before leaving, we check the Uniflow box to indicate flow only in the positive direction. To complete the programming, we next visit the growth rate term and give it a value of 0.1. And lastly, we must provide an initial value to the population stock, which we'll set to 1. We'll also check non-negative and uncheck full history, since that saves memory. Finally, we need a way to see the results of our simulation. We click the Displays and Controls tab and drag out a line graph, which we'll call Population Graph. To specify the content of the graph, first select it for the Property pane, then click the plus sign and pull down the Select menu and click on Population. This would be a good opportunity to save our work. First, name the model using the text box in the simulation pane. We'll call it Simple Pop. Next, pull down the File menu and select Save As. Numerus will choose a file name identical to the model name, but you can give the file any name you'd like. The last step we need to take before running the program is to specify the simulation parameters. Let's keep the end time at 20 model time units. Now a bit more about the choice of method. The reason we need this is because we are attempting to model a continuous process, but for practical reasons must make any changes at discrete time points. In reality, the flow value may actually be changing during the intervals between steps, and this factor may be lost in our computation. This figure illustrates the problem of choosing to assume a constant flow over an interval, which is the Euler method. Those who know calculus will recognize this diagram from the computation of an integral, which is in fact what we are computing. We can correct this by choosing a smaller dt with a narrower interval, but mathematicians Runge and Kutta came up with a formula that reduces the error by sampling partway through the interval. This figure, though not a precise representation, gives you some idea of how the error is reduced. Having changed the method to RK4, we can reduce the value of dt to 0.1, which is, we suspect, reasonable for this model. If more accuracy is needed, the dt value can be further adjusted. As we saw in the first tutorial, we click Launch to reveal the Numerus runtime frame, and we can run the model simply by clicking the Run button. Once again, a cursor sweep across the graph reveals population values at specific points, and clicking Table collects all of these into a table display. This design is rather inconvenient since we cannot change the growth rate without returning to the design canvas and adjusting the value of the growth rate term. Fortunately, Numerus provides a convenient tool for changing a fixed term into a slider. You simply select the term, visit the Tools menu, and click on Convert to Slider, and voila, the term is replaced by a slider with an initial value equal to the term value and a range and step size determined by Numerus to be reasonable, but which you can change. Relaunching, we can run the model several times with different growth rate values determined by the growth rate slider and see the results on the graph. In fact, if you select Auto Mode, the simulation will rerun each time you change the slider's value. We'd like to see the results at different growth rates together on one graph. So we return to the design frame and click on the graph and select Enable Compare. Now when we launch the program, we can run with multiple growth rates and compare results on the graph. Sweeping across with the cursor, we can see all of the different runs at once, and we can switch to the table view and see them in tabular form. As a final step, let's change the growth rate slider's properties. We can change the minimum and maximum values, step size, and initial value to whatever we want, just as long as the initial value lies between the boundaries determined by the minimum and maximum. The initial value can either be entered directly into the text field or set using the slider on the property pane. Now we can launch the simulation and see these new settings for the growth slider. So this concludes our tutorial. Next time, we'll build a more accurate population model and see some additional features that Numerus provides to help you do it. See you soon.